Hello friends and students, this lecture is on double integration topic. In this video, we are going to see what do we mean by double integration and what is the geometrical meaning of double integration, and then we will see few applications, that is area, how to find area by using double integration. So this video is for engineering mathematics 2. I have taken few examples from previous question papers from engineering mathematics 2 Pune University. So let's see, before beginning the double integration, let us see what single integral means. X is our independent variable and y is dependent variable. Y is depending on x. Y is equal to f of x is that relation by which y is depending on x. So here are the few examples by which x is depending on x. It could be x square, 3x plus 2, exponential, logarithmic, or any other relation. So let's see by a graph if that curve represents y is equal to f of x. So for every x we have plot y by that relation y is equal to f of x. That relation will draw this curve. So this is the relation, and if I want to restrict my x from x1 to x2, so this is the straight lines corresponding for x is equal to x1 and x2, and this is the curve for that limits for x. Then what I have done, I have considered a strip parallel to y-axis with very small width along x-axis. This dx is the width of that strip, which is very small, and the shape of this strip is rectangular type because on the top it is something like curved, but for very small width this curved surface will appear like a straight line. So this length is nothing but our y-axis, the coordinate of y-axis. So y-axis for this is y is equal to f of x, and width is very small, dx. So like this strip, I can draw infinitely many such kind of strips parallel to y-axis, and I am interested in finding the area of that strip. So the area of that shaded strip is length into breadth. So what is the length? Length, I am taking approximately the y coordinate. Y coordinate is f of x for that shaded strip. And what is the width? Width is dx. So the area is length into breadth. So this is the area of that single strip I have taken. Like that, I can take infinitely many strips which approximate that region, this region, which approximate this region, the region under that curve, the x is equal to x2, x is equal to x1, and this x-axis. So like that, I am going to add the area of all such infinite strips. So it becomes summation of f of x into dx. Area under the curve, since my x is continuously running between x1 and x2, it's not going to leave any single value between this interval x1 and x2, so that because of continuity I can replace this summation by integration sign. So that summation is replaced by integration of area of that single strip, and that strip is running from x1 to x2. So this integration from x1 to x2 gives me the area under that curve x-axis, and the x is equal to x1 and x is equal to x2. So this is the geometrical interpretation of single integration, which says that single integration is nothing but area under the curve. Let's move forward. Now for double integration, I have to take two independent variables x and y, and z is dependent on x and y. So this is the relation z is equal to f of x, y. Now I have to draw my diagram in 3 dimensions. So this is the diagram, x-axis, y-axis, and for every point x and y, my z is depending on the values of x and y. So that represents my domain. So for simplicity, deliberately I am taking my domain a rectangular shape, and that point xy represents a point in my domain. So for every such point, I am going to plot z. That z will represent a surface in 3D. The second diagram says that for every point I have lifted a z axis, I have got a z coordinate which lift that surface along z axis. So this is the 3D structure I have obtained just by dropping a projection of that surface on xy axis, which will be bounded by my domain boundaries. For simplicity, I have taken domain as a rectangular shape, and that surface could take any shape in 3 dimensions. So I have taken a projection of that surface on xy axis. So this diagram tells me that there is some volume in this structure. We have to find that volume. Let's move further. So here we have one more diagram of the same structure. Now what I have done here is I have fixed one y. So I am fixing y coordinate, say y0, and I have drawn a straight line for that fixed y. I have drawn a straight line parallel to x-axis. Then I'm going to draw a parallel line from that fixed y parallel to z-axis. You can see from that diagram, it represents a sheet inside that 3D structure. It represents a sheet kind with no thickness. So there is no thickness for that sheet, and we are interested in its area. On that sheet, y is constant. So f of x y0 is in only one variable, because y0 is a constant, and that function f of xy is depending on only one variable, that is x. So for single integration, area of that sheet is given by this equation. We have seen this earlier. Single integration gives me that area of that one-dimensional structure, that is a sheet in this, a single sheet with no thickness in this diagram. So the integration from x1 to x2, my x is running from x1 to x2 here. In this case x1 is 0 and x2 it could be any point on x-axis. So integration of this height, this is height and this is the dx is our the width, length and the breadth. So this dx is the width of that single strip drawn like this, and the length is f of x y naught, and we are integrating this strip. So this single integration gives us the area of that sheet. Now we will change y, that is we will consider a small thickness for that sheet. So this is the diagram for giving height to that sheet given thickness. So consider dy a very small length along y-axis, which is the thickness for the sheet. Now we are interested in volume of that sheet because we have some thickness. Earlier we have length and breadth, now we have thickness also. So that slab kind structure is going to have, so this structure, this slab is going to have some volume. So what is the volume of that slab, of that sheet? It is given by this area into height. What was the area of that sheet, of that slab? It is this thing, and into the height. So this is the volume of that single slab structure, and I can draw infinitely many slabs for this complete structure in 3D. So what is the volume of this? We know the volume of this. We have to add all the volumes of that slab to obtain the volume of the surface and the xy plane, the volume under that surface. So volume of the whole structure is given by, so you have to integrate so instead of adding again that y, this y is a continuous, so I'm not going to take summation, take integration directly because of continuous variable. So integration of this with respect to dy of the volume of one slab gives you the total volume of the structure bounded by that surface and the coordinate planes. So with this explanation, we are clear that double integration gives volume under that surface bounded by the coordinate planes and the domain. So this says that single integration gives us area under that curve, double integration gives volume under that surface. Now how to solve double integration? Here I have a very simple example. Solve the double integration. Solve the double integration of x into y square dx dy, where the domain is x is running between 0 to 2 and y is running between 0 to 1. So let I is equal to double integral x y square dx dy. It represents some volume under that surface. So if I try to plot this function f of xy, it will take shape something like this. And I want to find the area under this say under this surface. So this is the area I am interested to calculate. It's like a tent, you can imagine this. So I is equal to, x is running from 0 to 2 and y is equal to y is running from 0 to 1, integration of xy square dx dy. Now here I can see that this is very easy to solve because integration limits are constant on both integration, and my function xy square, it has only one term, so I can separate it very easily. So dx will separate, taking its term x and taking its integration. So here it is separated, multiplication sign is in between, and y will separate with its term and its integration. So y square. This happens because my limits are constant and my function, they are ready to separate. And I have carried out the integration. So this is the volume under that surface, 2 by 3 cubic units. Let's see one more example. So evaluate double integral of x square y square dx dy over the positive quadrant of x square plus y square. You can see these examples, they are frequently asked in Pune University exams for engineering mathematics 2. Okay, so let's try to solve. I have denoted it by I, where R is the positive quadrant. Now there is two or three ways to solve this question. First is, I can draw the graph of the domain where I have to carry out this double integration. So this represents a circle and I'm evaluating that double integration in positive quadrant, first quadrant. So this is the diagram. So one way is I can consider a parallel strip to y-axis, and this strip is moving in this direction. So it is moving in this direction. So along this strip, so consider a parallel strip to y-axis. Along this strip, x varies from 0 to 1. We can see that x is running from 0 to 1, and y is running from 0 to y. Y is moving like this. So y is stopped by this curve on the top. The name of this curve is y is equal to under root 1 minus x square. So after finding the limits, let's put it into the integrals. This is what I have got after putting the limits, but I'm not going to solve this by this method. Whenever I see x square y square and this circle equation, I always use a radial strip. I always try to use polar coordinates. So here I have one more diagram for the same region, but this time I have changed my strip. I have taken a radial strip. Consider a radial strip. Along this strip, theta will run over the first quadrant, that is from 0 to 90 degree, and r can take value from 0 to 1. It cannot exceed that circle. That circle is of radius 1. I have to shade that complete region. So r is running from 0 to 1. So with these limits, I have reached up to here that integral I is r 0 to 1, theta 0 to pi by 2, x square y square. I cannot write x square y square dx dy once I have substituted the limits in r and theta. So I have to think of the polar coordinates. So x is equal to r cos theta, y is equal to r sin theta, and dx dy is r dr d theta. So I is equal to, so putting x square and y square is equal to r cos theta and r sin theta, I have total r raised to 5 cos square sin square dr d theta. Try to solve this. So this is easy to solve. I have used reduction formula to solve that integral. Answer is pi by 96. Use reduction formula. So here we have one more example. Oh, okay, that's the application of double integration, finding the area between the two curves. Find the area bounded by the parabola x square y square and the line y is equal to x square. So that's the application of double integration. So you have to integrate 1 instead of f of xy, you have to integrate 1 to obtain the area. So what is the region? Region is bounded by that parabola and that straight line. So r is the region between y is equal to x square and y is equal to x. This is the diagram. So y is equal to x square is this, and this is the straight line. Find all the intersection points by solving y is equal to x square and y is equal to x simultaneously. Solve them simultaneously to obtain the intersection points 0, 0 and 1, 1. So after solving, so this is the intersection point and this is the second intersection point. So instead of f of x, you have to integrate 1 to obtain the area. So consider a strip parallel to y-axis. Along that strip, you can see that along this strip, x is varying from 0 to 1 and y is varying from this point to this point, from this point to this point, from this to this. So what is the lower limit for y? Lower limit for y is this curve and the upper limit for y is this curve. So y is running from x square to x. So that area is, put the limits, x is running from 0 to 1, y is running from x square to x. This is how I have solved this. I cannot do this because I have realized that integration does not have constant limits. I cannot separate this. So I have to carry out that integration first, which is having variable limits, and the constant limits will be evaluated in the end. So I am keeping x integration for the end. So let's solve dy first. So let's solve 0 to, so I have kept x integration outside and I'm evaluating dy and its integration first. So integration of dy is y. Put the limits. So I have x minus x square dx and the integration of x. Do all the integrations, you will get 1 by 6. So here we have one more example. I think this is the last. Yeah, this is the last example. So evaluate this integration, and I'm not going to draw any diagram for this. You have to distinguish such kind of examples where you have to draw diagrams. Again, I can see 1 plus x square, but I'm not going to draw a circle here because it's not a circle. I have to use substitution in it. So evaluate this double integration x. Okay, the integration having variable x is for y. You have to remember that the integration having x variable on it is for y, and the remaining integration is for x. So after deciding that I is equal to, x is running from 0 to 1, y is running from 0 to 1 plus under root 1 plus x square, you can see that 1 plus x square and 1 plus x square, there is they are in limit and integrand also. So obviously with no thinking I'm going to substitute it. So 1 plus x square is equal to a square, and a is under root 1 plus x square. So this will, after substituting, I will get this. X is running from 0 to 1, y is 0 to a, and dx dy upon a square plus y square. Sorry for this. Okay, so this integration, I will keep this integration to solve in the end. Let's solve y first, because y integration is having variable in it. So I have taken that integration inside that bracket to solve it first. So integration of dy upon y square plus a square, it is 1 upon a tan inverse y upon a. So this is what I have written, and its limit. So after putting limits, put y is equal to a, so it becomes tan inverse 1, put y is equal to 0, tan inverse 0 dx. So tan inverse 1 is pi by 4, 45 degree, and tan inverse 0 is 0, so this is not in that equation. It goes, and this is constant, so it will jump here like pi by 4, so I have written here. So pi by 4, and what is left over, integration 0 to 1 upon a dx. So pi by 4 outside, pi by 4 outside, 0 to 1 dx under root, what is a? A is under root 1 plus x square, so I have substituted it. So 1 upon a, this 1 upon a is under root 1 plus x square. Integration of this thing is log x plus under root x square plus 1. Then I'm going to substitute I'm going to put the limits. X is equal to 1, and this is 1 plus 1, so this is 2 under root 2 and log 1. Once you put 0, this is 0, this is 0, it is log under root 1, so log 1 is 0, so this is gone. So this says that integration of this thing is pi by 4 log 1 plus root 2. This is all about double integration. Thank you so much.